This is the third video in the series on volume that we'll be doing for calculus. In this video, we're going to focus on calculating the volume of a rotational solid using the method of cylindrical shells. This method is very similar to that of discs and washers. There's just a few slight alterations that might actually make it a little bit more preferable to use over discs and washers. Also, our integral is going to be slightly tweaked. In this video, we're going to cover some notes on just how it comes up or why it would be more preferable. And then there are 4 examples. Each one has a couple parts to it. To save time, we will be using a calculator for the bulk of example 3 and example 4, but examples 1 and 2 should be pretty straightforward and easy enough for us to do just some straight up integral calculus. So let's start with the cylindrical shell method. So in this section, we present an alternative to the method of washers discussed at the end of 5.2 in the second video. So if we let R denote a region bounded by the graph of y equals f of x and the x-axis on the interval from a to b where 0 is less than a, which is less than b, and f of x is greater than or equal to 0 on a and b. So basically all that's saying is that this entire function is contained, but this entire integral will be contained within the first quadrant. If we take that region, which is this purple region right here, and we rotate it or revolve the region about the y-axis, we're going to get this solid. So we take, and this is the original solid right here, or the original curve, and we take it and we rotate it around here. Now, if we wanted to calculate the volume of that, we already do have 2 methods under our belt, which we could use to figure out that volume, and seeing as there is a hole in this, we would probably end up using washers anyway. The main thing that we do have to remember with washers is that our long side of our rectangle, or our representative rectangle, would be perpendicular to the axis of rotation. And then we'd have to find an inner radius and an outer radius. What we do see is that when we do try to find the volume of a solid using a washer, it's awkward, since we need to break the region up into several pieces. If we try to draw a horizontal rectangle, we can do a horizontal rectangle just fine right here, but if we go higher up in the region, right around this area, there's no way that we can go entirely across the interval from A to B using a horizontal rectangle. Right there. And so what we would end up having to do is we would end up having to break that into several different integrals with different limits, and that would be really complicated. Alternatively, we can partition A to B into n subintervals of equal length delta x, which is b minus a over n, which we know is how we set up a Riemann sum. And on each subinterval, we pick a point c sub I and construct a rectangle of height f of c sub I. And the thing that's going to happen is that this rectangle is going to be parallel to the axis of rotation. So the length of our, or the long side of our representative rectangle is going to be parallel to the axis of rotation. Revolving this rectangle around the y-axis, we get a thin cylindrical shell. So now, instead of having a horizontal rectangle, which we just tried to create up top, and we weren't able to do, now we have a vertical rectangle, which I know that this long side here is going to be parallel to the axis of rotation. And when we take this and we rotate it around the y-axis like this, what we end up with is we end up with a cylindrical shell like this. And it's called a cylindrical shell is because it's a hollow cylinder. It kind of looks like a pipe. And what we can do is we can actually figure out the volume of the cylindrical shell. Let me just go to the next page. Okay, so to find the volume of that cylindrical shell, imagine cutting the cylinder from top to bottom. So we take this and we slice it right down the top, and we flatten it out. And when we flatten out the cylinder, we get this long rectangle. Okay, and you should have a thin rectangular sheet, and that the length of this rectangle is equal to the circumference of the whole cylinder, which is going to be 2 pi times the radius of that cylinder. And since the radius is going to be that 2c sub I, or that c sub I, the circumference is going to be 2 pi times c sub I. And so the volume of the ith cylindrical shell is approximately length times width times height, which we know for any cylindrical shell is going to be that, or any cylinder is going to be that, which is going to be 2 times the radius times the thickness of the shell times the height of the shell. And so the length of the shell we know is 2 pi c sub I. The thickness is always going to be delta x, and the height of the shell is going to be f of c sub I. Okay, so if we want to just sort of annotate this here is going to be the length. This part right here is going to be the thickness, and the thickness is always delta x. And then the height is going to be the height of the rectangle, which we already know is f of x sub I, or f of c sub I. Now, when we start stacking cylindrical shells in sort of a concentric circle around each other, what we end up doing is we're adding up all the volumes of all of these cylindrical shells. And so the volume of the solid can be approximated, and again, we're always starting with an approximation when we're doing these volumes and all of these integrals, by taking the sum from I equals 1 to n of 2 of c sub I, f of c sub I times delta x. And this is so where this is the length, the height, and the width. And we know that whenever we have this 2 pi, and it's a constant, and we can pull out the constants, and we're going to do that in the next slide actually, but as we've done countless times before, we can get the exact volume of the solid by taking the limit as n goes to infinity, and we know that if we increase n to infinity, the thickness of each cylinder would become infinitely thin, and it would better approximate the curve. And so that what we can do is we can take this limit of a sum and we can rewrite it as a definite integral from a to b of 2 pi times some radius, which for the most part will be either x or y, and we'll talk about that in a sec, times the height of the cylinder, which will be f of x, times the thickness, which will be dx. And dx really doesn't really do anything for us in the integral, but it'll tell us which integral with which respect we're integrating. Now, since the axis of rotation can be horizontal or vertical, and the radius itself can be a function, and we'll talk about what that means in an example or two, we generalize the volume formula into two separate cases. And so we have the shell method, where we have a horizontal axis of rotation and we have a vertical axis of rotation. And so volume is equal to 2 pi times the integral from, this case they give us e to d, but it's always from a to b, of p of y, which is going to be our radius, times h of y, which is going to be the height, dy, which is the thickness, or if it's a vertical axis of revolution, which we'll start with, it'll be p of x, which is going to be the radius, times h of x, which is the height, times dx, which is the thickness. Okay. Visually, it looks like this. So with a vertical axis of revolution, it's always going to be this inner radius here, which for the most part, if it's a vertical axis of revolution, is going to be equal to x, times the height of the rectangle, which will be the height from wherever your bottom end is all the way up to the curve, times delta x, which is just going to turn into dx, and then we'll integrate over that interval. Similarly, if it's a horizontal axis of revolution, this p of y, which is going to be our inner radius, is just going to equal y. It might change a little bit, but we'll talk about specific cases for that. Times the length of the rectangle, or the height of the rectangle, which goes from the lower end of our area all the way up to the curve. And then we'll integrate from over this area. Okay, so let's try an example with it. Find the volume of solid of find the volume of the solid of revolution formed by revolving the region bounded by the graph of y equals x minus x cubed, and the x-axis from 0 is less than or equal to x, which is less than or equal to 1, about the y-axis. So what you should see is that the y-axis is my axis of revolution. My rectangle here is vertical, so we actually are going to use a vertical shell to do it, or to find the volume. And this distance here, or this inner radius, is going to be x, and it's usually always going to be x. We'll talk about a couple examples where it's not going to be that, or it's going to be just tweaked a little bit. And then the height is going to be the height of the rectangle from the x-axis down here up until it touches the curve, which is going to be x minus x cubed. So when we do the volume will be the integral or it'll be 2 pi times the integral from 0 to 1 of the inner radius, which is x, times x minus x cubed dx, which is going to be equal to, and we're going to distribute out the x and clean everything up before we actually do our antiderivatives. So it'll be 2 pi times the integral from 0 to 1 of x squared minus x to the fourth dx. Taking the antiderivative of the inside, it should be 2 pi times x cubed over 3 minus x to the fifth over 5. And that's going to be evaluated from 0 to 1. Since 0 is my lower limit, I don't actually have to evaluate it. So this is going to be 2 pi times 1/3 minus 1/5. And without having to deal with cleaning it up, this is actually going to be equal to 4 pi over 15. So the volume of the solid, when we rotate this curve around the x-axis, or around the y-axis, sorry, is going to have a volume of 4 pi over 15 cubic units. Let's try part B. Use the method of cylindrical shells to find the volume of the solid formed by revolving the region bounded by the graphs of y equals x and y equals x squared in the first quadrant about the y-axis. So setting these two curves equal to each other, we see that they cross at x equals 0 and x equals 1, so those will be my limits of integration. I have a vertical rectangle, and it's parallel to the axis of revolution, which is the y-axis. So again, I'm going to use vertical shells. You should always just try to take time and identify which method you're going to use and just write it to the top so you don't forget. And I know that the radius is going to be x again, and the height of the rectangle is going to be the top curve minus the bottom curve. So it's going to be this x minus x squared. So the volume of the cylindrical shell is going to be 2 pi times the integral from 0 to 1 of the inner radius, which is x, times the height of the rectangle, which is going to be x minus x squared dx. Distributing out, we should get 2 pi times the integral from 0 to 1 of x squared minus x cubed dx. Taking the antiderivative of the inside, it'll be 2 pi times x cubed over 3 minus x to the fourth over 4. And we're going to evaluate that from 0 to 1. Since 0 is my lower limit, I don't need to evaluate it. So it'll be 2 pi times 1/3 minus 1/4. And when I make like denominators and I subtract everything out and distributed my 2 pi, the answer I will get is pi over 6. And so the volume of the solid that's created is going to have a volume of pi over 6 cubic units. Okay, let's try example 2. Okay, so you're always allowed to use either method, washers or shells, to compute the volume of rotational solids. It is up to you to determine which method will be better for the given situation. So here are some guidelines to help you out, because I know that this can be really complicated. So the first thing you're always going to do before you do anything is orient your rectangle. So always draw a representative rectangle for your revolution. Start with a vertical rectangle. It's good to start at the same place every time. And if the rectangle cannot be drawn, so it's always between two different lines, you have to turn it to a horizontal rectangle. And that should do it. And then depending on the situation, depending on that rectangle's relationship to your axis of revolution, it'll tell you whether or not you're going to end up using a shell or a washer. So if the longest side of your rectangle, if the long side of your rectangle is parallel to the axis of rotation, you're going to use the shell method, which is denoted by this picture here. And if the long side of your rectangle is perpendicular to the axis of rotation, you're going to use the washer method. So you should see that this is my axis of revolution, and the long side of the rectangle is perpendicular to the axis of revolution, whereas in this one it's parallel, which will involve using two different methods for integration. So remember, the shell method volume is 2 pi integral a to b of p of x, h of x, dx. And then the washer method was volume equals 1 pi times the integral from a to b of the outer radius, rx squared, minus the inner radius. So they're very different methods, and one will always be better than the other. So let's try example 2. Find the volume of the solid formed by revolving the region bounded by the graphs y equals x squared plus 1, y equals 0, and x equals 1 about the y-axis. So again, the y-axis is right here, so that means that this is my revolution, or my axis of revolution. I need to orient my rectangle. So the first thing I need to do is I need to draw a representative rectangle. I'll start with a vertical. So go like that. And I notice that my rectangle is completely is between two different curves, or two different lines throughout the whole interval between 0 and 1. So I'm going to use a vertical rectangle, and it's parallel to the axis of revolution. So this is going to be a vertical shell. I know that my limits of integration should be between 0 and 1 then. My inner radius, or my radius here, is now, since it's a shell method and it's vertical, the radius will be x. And then the height of the rectangle will be x squared plus 1. From that, I should be able to write my entire volume formula. So volume, using vertical shells, is 2 pi times the integral from 0 to 1, my lower limits, or my upper and lower bounds, the radius of the shell, x, times the height of the shell, x squared plus 1, dx. Let's distribute. So you get 2 pi times the integral from 0 to 1, x cubed plus x, dx. Antiderivative of the inside, it's 2 pi times x to the 4th over 4 plus x squared over 2. That's being evaluated from 0 to 1. I don't need to evaluate the lower limit since it's 0. So the volume of the shell will be 2 pi times 1/4 plus 1/2. And this will simplify out to a volume of 3 pi over 2 cubic units. Okay. So far, we've been really fortunate in having our axis of revolution be either the x or the y-axis. In this case, I think it's been pretty much the y-axis the entire time. So let's change that up a little bit. Let's find the volume of the solid formed by revolving the region bounded by the graph y equals 4 minus x squared, and the x-axis about the line x equals 3. So let me pull this picture down here just a little bit to work with. Make it a little bigger. This line right here is my axis of revolution. This is x equals 3. Looking at my graph of my picture, I know that I'm going to start by drawing a vertical rectangle. So I need to orient my rectangle. I see that my rectangle is going to be on the curve for the entirety of the interval on one side, and it's going to ride the x-axis on the other side, so I think that I'm going to end up using a vertical rectangle. My limits of integration look like it's going to go from about -2 to +2. And since I'm using a vertical rectangle and it's parallel to my axis of revolution, I'm going to use a vertical shell. Okay. So the trickiest part about this is the radius. Since the radius is not the x or the y-axis, it's this line x equals 3. We have to start using a little bit of critical thinking. We have to think about, well, what is the distance between this line x equals 3 and this rectangle? And so what it's always going to be is, I know that the distance from the rectangle to the y-axis is always going to be x. And what it's always going to be, to figure out what these radius or radii are going to be, it is always going to be if it's a vertical shell, it'll always be the right minus the left. And if it's horizontal, it would be top minus bottom, but we'll deal with top minus bottom in a second. What I mean by right minus left is that the line that is furthest to the right will be the first thing that we subtract. And it'll be not over left, it'll be right minus left. Okay, so the right curve is 3, x equals 3, and then this distance is x. So the radius is going to be the right line, which is 3 minus x. If it were switched, and we were rotating about the line x equals -3, then these would have switched. It would have been x minus -3, which would be x plus 3, but we'll deal with one like that in a minute. The height of my curve is going to be y equals 4 minus x squared. And so the volume of the shell is going to be 2 pi times the integral from -2 to 2 of the radius, which is 3 minus x, times the height of the parabola, or the height of the rectangle, 4 minus x squared dx. Cleaning up the inside, it'll be 2 pi -2 to 2 of, when we FOIL this out, what we end up with is x cubed minus 3x squared minus 4x plus 12 dx. Taking the antiderivative of the inside, 2 pi times x to the 4th over 4 minus x cubed minus 2x squared plus 12x. And that's being evaluated from -2 to 2. For the sake of time, I'm not going to have you guys plug that in, so I'll tell you, after you evaluate 2 in this and subtract out when you evaluate -2 in and multiply by 2 pi, the volume of the solid will be 64 pi units. And you can get that using a calculator. So let's try a couple more examples. They're going to be a little bit more complicated. So example 3. Let R be the region bounded by the graphs of y equals x and y equals 2 minus x and y equals 0. So that's going to make that blue triangle in the center. Compute the volume of the solid formed by revolution r about the line. For A, it'll be y equals 2. For B, it'll be y equals -1. And for C, it'll be x equals 3. So first off, before we deal with jumping into A, B, and C, let's just take a look at our picture here and sort of pick it apart. Didn't separate it. So I have this here, this line here, and that's y equals x. I know that this line right here is y equals 2 minus x. And I know that the bottom is going to be the x-axis, which is y equals 0. And the first thing I need to do is I need to orient my rectangle. So if I draw a vertical rectangle here, I should realize that there's no way that I can draw a vertical rectangle so that it'll be consistently between two curves the entire time. I would have to break the integral here and do two separate integrals to find the volume. And that's going to be really, really irritating, especially when I have to start revolving it around an axis. So what I need to do is I need to turn my rectangle sideways. So I'm going to have a horizontal rectangle. Okay, so you're going to have a horizontal rectangle. What I can tell you is that the limits of integration will be the same for each one of these since we're using a horizontal rectangle. But in order to use a horizontal rectangle, I have to solve for x and then find new limits. So taking each curve, y equals x is actually already solved for itself, so I don't have to do anything to it. But y equals 2 minus x needs some work. So solving this for x, we should get negative x equals y minus 2. And so x equals 2 minus y. And so I'll use this equation and this equation. And then also finding new limits, I know that I'm going to go from 0 here and the y coordinate of where they cross up here, which is actually going to be y equals 1. So my limits are going to be from 0 to 1. So keeping that in mind, so I have y equals x as one curve, x equals y as one curve, x equals 2 minus y as the other curve, and my limits are going to be from 0 to 1. Okay. For the line y equals 2 to do this rotation, I notice that this is my axis of rotation. I still have a horizontal rectangle, which means I'm going to use a horizontal shell. I need to find the radius. And so since this is a horizontal shell, the radius is going to equal the top line minus the bottom line. Okay. The top line is y equals 2, so it's this value of y equals 2, or it'll be the top value minus the bottom value. And then the bottom value is going to be this y distance for my radius. And so my radius in this is going to be 2 minus y. The height of my rectangle, or the length of my rectangle, which we'll call h of x, is going to be this right line minus this left line. So it'll be 2 minus y minus y, which in this case is going to be 2 minus 2y, which we can use this over and over again for each one of our integrals and each part. And so the volume is going to equal 2 pi times the integral. Our limits were now 0 and 1. The radius is 2 minus y, and our height is 2 minus 2y dy. We can take this and plug it into a calculator, and what we will end up with is a volume of 8 pi over 3. The real thing that I'm trying to get out of these examples is trying to figure out the length of the radius. The length of the rectangle is going to be consistent throughout the whole thing, but the radius will change. All right, so let's try part B. So it's y equals negative 1. So again, we have a horizontal rectangle. I have a distance of y for my radius, and then I have this line y equals negative 1 down on the bottom. Radius is going to be top minus bottom top value minus bottom value. On the top value, I have a y. On the bottom value, I have a -1. So it's going to be y minus -1, which is y plus 1. My height, or my h of x, is still the same as it was for the last part, which is 2 minus 2y. To find the volume of the solid, it'll be y, or volume equals 2 pi times the integral. It's 0 to 1. And it'll be the inner radius, which is y plus 1, times 2 minus 2y dy. And using a calculator to do that, that's still going to be a horizontal shell. It should be 8 pi over 3. And I think I made a mistake. On the last slide, yes, I was wrong. The volume of your solid was not 8 pi over 3. When you plug this into a calculator, you're going to get a volume of 10 pi over 3. I'm sorry. So 10 pi over 3 for A, 8 pi over 3 for B, and then let's try C. So again, I still have a horizontal rectangle. But what I should notice is that if this is my axis of rotation, it's actually perpendicular to my axis of rotation. So I have a horizontal rectangle that's perpendicular. This is actually going to be a washer, which I know for washers, volume is pi times the integral from A to B of the inner radius, or sorry, the outer radius squared minus the inner radius squared. In this case, it'll be y. But we do it the same way. So the outer radius, or r of y, which will be from here all the way out to here. And then my inner radius, which will go from here to here. My outer radius will be 3 minus y. And my inner radius will be 3 minus 2 minus y. Using a volume for a washer, it'll be 3 minus y squared minus 3 minus 2 minus y squared dy. And I can put that whole thing into a calculator, and what the volume will be of that washer will be 4 pi cubic units. That pretty much sums up all of the work that we can really do with cylindrical shells. I understand that it is a little bit more complicated. You might want to watch this a couple times. Please check the email for a problem set that you can work on using cylindrical shells. Remember, you want to identify what kind of shell you're using first, and then go from there.